Verify, ready to resume the count and say go for launch. OTC, tank and boosters are go. TTC, TTC is go for launch, sir. And thank you.
Velkommen til RumSnak, en podcast om rumnationen Danmark og de danske rumaktiviteter inden for både forskning og forretning.
Mit navn er Tina Ibsen.
Jeg hedder Anders Høgh Nissen.
Spænd selen og start nedtællingen. Vi er klar til affyring.
2, 1, 0 and liftoff.
All right, lift-off and the clock has started.
Velkommen til RumSnak, hvor vi denne gang skal på besøg på Geologisk Museum i København.
Ja, for der ligger nemlig Center for Star and Planet Formation, eller StarPlan, som det hedder mellem venner, hvor de, som navnet antyder, prøver at blive klogere på, hvordan nye stjerner og planeter bliver dannet.
Forskerne på StarPlan de bruger mange forskellige metoder i deres arbejde, men en af dem er kemisk analyse af meteoritter, og ikke mindst prøver fra asteroider som dem fra Osiris-Rex-missionen og asteroiden Bennu.
Vi har talt med centerleder og professor Martin Bizzarro, som både viser rundt på laboratoriet og fortæller om de nye teorier om jordens dannelse.
Ja, for måske er det sådan, at jorden blev dannet på få millioner år, i stedet for de 50-100 millioner år, som vi hidtil har troet.
Det er der i hvert fald noget, der tyder på, og det er noget af det, vi dykker ned i denne omgang.
Vi skal dog også have et par aktuelle nyheder, og selvfølgelig lidt baggrund om planetdannelse og asteroidestøv. Alt sammen lige her i RumSnak. Jeg hedder Tina Ibsen.
Og jeg hedder Anders Høgh Nissen. Velkommen til.
3, 2, 1, 0 and liftoff.
Og vi lægger altså ud med et par korte nyheder fra rumland, inden vi kaster os over asteroideprøver og planetdannelse. Så Anders, take it away.
Ja, måske skulle vi lige sige, at vi jo ikke havde rumnyheder med i den seneste episode, fordi vi havde proppet programmet med forskere og jo altså en direkte snak med Andreas Mogensen oppe på ISS. Så der er et par nyheder, der har et par uger på banen. Til gengæld så har jeg faktisk, jeg synes, jeg har begrænset mig relativt meget taget betragtning, at det er nu en måned siden, vi havde nyheder med, ikke?
Det er rigtigt. Du er meget dygtig, Anders.
Tak. 52 år og bekræftelsessyg, det er mig. Vi lægger ud helt tilbage den 18. november, hvor SpaceX for anden gang foretog en testflyvning af den 5.000 tons tunge Starship-raket. Som man måske husker, så endte den første affyring tilbage i april, hvis jeg ellers husker ret, ganske kort tid efter affyringen, da Starship bragte sig til eksplosion på grund af sådan et automatiseret sikkerhedssystem knap 40 km oppe på grund af tekniske problemer. Den anden testlaunch her den 18. november, den forløb heller ikke helt efter planen, men dog noget bedre. Starten gik godt, alle 33 Raptor-motorer tændte som de skulle, og Starship forlod jordens overflade i ganske fin stil, men da andet trin skulle skilles fra boosterraketten op i 70 km højde, der begyndte der altså at opstå problemer. For det lykkedes ganske vist at starte de her Raptor Vacuum-motorer på andet trin, der var fint på vej videre ud i rummet, men første trin eksploderede så kort tid efter, i stedet for at tage en tur rundt om planeten, sådan som det egentlig var meningen. Og så i en højde af 148 km, der blev andet trins selvdestruktionssystem også bragt til eksplosion, eller det bragte andet trin til eksplosion. Ikke desto mindre så betragtes den her anden testflyvning dog som en succes, selvom det hele på nogen måder i hvert fald en eksplosiv succes, ikke? Fordi affyringen skete efter bogen, og det var en af de vigtige ting, man gerne ville have testet, og også fordi man altså nåede at sende trin 2 videre fra boosterraketten, sådan som det skulle ske. Jeg tænker, at der nok er brug for et par testflyvninger mere, og den næste forventes faktisk allerede i begyndelsen af næste år, så må vi se, hvor langt Starship når denne gang.
Du tager ikke en billet på testflyvning nummer 3? Jeg
tror faktisk, det er en af dem, hvor selv hvis jeg blev tilbudt en plads oppe i toppen, så tror jeg vil betakke mig, trods alt.
Selv en af dem. Jeg tænker, der er mange af de der test, hvor jeg vil sige, jeg synes lige, I skal prøve det en 10-15 gange.
Kan vi sende en mannequin op i stedet? Ja. Hvad er du med til os?
Vi skal en tur til Sunny Wales. Fordi på mit gamle universitet i Aberystwyth...
Kan jeg bare sige dit gamle universitet, eller det universitet, som du har gået på?
Mit gamle universitet.
Dit gamle universitet.
Det er mit gamle universitet.
Alright.
Jeg brugte mit 3. år i Wales som min studie, og det var her, hvor jeg forelskede mig i rumvejr og solstorme. Men det er faktisk ikke det, min nyhed handler om, for en gangs skyld. Du
kan bare have lov til at nævne, at du har gået på universitet i Wales. Ja.
Nej, det var fordi, at jeg sad faktisk til morgenmaden og lyttede nyheder fra BBC, og så lige pludselig kom der a news from Aberystwyth University. Og sådan, hvad er det?
Det sker ikke hver dag.
Nej, det er sjældent. Så jeg blev selvfølgelig nødt til at tage den med her.
Naturligvis.
Det handler ikke om rumvejr, nordlys. Vi skal nemlig en tur til Mars og Mars-roveren Rosalind Franklin fra ESA, som jo har været igennem nogle ret turbulente år, kan vi vist godt sige. Først så var roveren et samarbejde mellem Roskosmos og ESA, men efter krigen i Ukraine, der blev samarbejdet med Rusland jo så af gode grunde stoppet. Og derfor så har ESA nu skulle finde både penge og ekspertise til at fortsætte det her arbejde på roveren. Noget af det arbejde, det er indgået i samarbejde med NASA, men der er altså også kommet nye partnere ind fra europæisk side. Og der er faktisk kommet ret mange ting fra Storbritannien med. De har virkelig satset på den her mission. Og en af de her partnere er så altså universitetet i Aberystwyth, hvor de skal bygge et infrarødt spektrometer, der skal sidde i hovedet på roveren, kan man sige. Instrumentet, det kaldes ENFIS og betyder regnbue på walisisk.
Vidste du det i forvejen?
Nej, det gør jeg faktisk ikke. Jeg kan huske meget, meget få ord. Jeg kan huske bus, staves BWS, ja, og siges bus.
Det er jo nærmest snyd.
Og så boede jeg på Cambarton Road. Så det var også dobbelt L, siger man. Altså,
okay.
Der er lidt ting, jeg har taget med i sproget, men ikke meget. Aha. Nå, tilbage. Yep. Lige nu der går arbejdet med at designe og bygge det her instrument, og sammen med de andre kameraer, der også er i, kan man sige, roverens hoved, så skal de bestemme gode steder at bore i Mars, fordi noget af det, mange er begejstrede over, og man kan sige, hele sådan kronjuvelen på Rosalind Franklin, er nemlig de her 2 meter lange bor, der vil kunne lave nogle meget dybe boreprøver på Mars, på jagt efter liv, og hvad det er for nogle forhold, der er langt under overfladen. Fordi man mener, at hvis der er liv stadig, så er det nok i nogle lommer under overfladen, et stykke under overfladen i hvert fald, eller det kan være her, hvor livet har overlevet længst tid. Så det er noget af det, man arbejder med, og går alt efter planen, så er den nye dato eller tid for opsendelse, det bliver i 2028.
Der er alligevel lang tid til,
så der er noget tid til, ja, men det er jo igen også, man skal jo redesigne flere instrumenter, man skal have et helt nyt landingssystem, fordi den skulle være sendt op med en russisk raket, ikke? Altså så bare det der med, at den skal designe og tilpasses et andet landingssystem, betyder enormt meget.
Ja, det er vildt.
Og så har man måttet tage rigtig mange instrumenter ud, så det er ikke bare sådan lige.
Det er ikke sådan lige container shipping.
Nej, præcis. Nej. Anders, jeg tænker, at vi holder os ikke til Starship den her gang, selvom du sagde, at du ikke havde mange.
Jeg sagde ikke, at jeg ikke havde mere end en. Jeg sagde bare, at jeg ikke havde mange. Vi bliver bare lige nødt til at nævne, fordi vores seneste episode handlede jo om Andreas Mogensen og hans forskning, og op på ISS og den anden forskning, der foregår deroppe, men altså især Andreas'. Og her i slutningen af november, der lykkedes det jo ham at tage flere billeder af de her sjældne blå og røde lyn deroppe fra. Det var jo en af de ting, der lykkedes for ham på den der meget korte tur, han havde tilbage i 15, at han faktisk fik taget ret fine billeder af de her blå lyn og røde sprites, som man kalder dem, når de opstår højt op i atmosfæren. Han havde så har den her gang et meget bedre kamera med, som kan tage over 100.000 billeder per sekund. Og det har altså gjort det muligt at fange de her lyn, mens de opstår, så man nærmest kan se deres udvikling. Det her kamera er en del af det, der hedder Thor Davis-projektet på DTU, og består af en særlig sensor, som monteres oven på et videokamera, som indsamler data, som så senere kan skabe de her billedsekvenser med høj tidslig opløsning.
Jamen, jeg så noget, det ser sådan ret funky ud, lige sådan nogle pixels, der sådan bevæger sig op.
Ja, det er ikke billeder, der billedmæssigt har super, super høj opløsning, men tidsmæssigt har de høj opløsning, og det er jo meget vigtigt, fordi det er ekstremt hurtige fænomener, det her, ikke? Det er jo også relateret, det her arbejde, til den store ASIM-mission og instrumentet, der har siddet uden på ISS siden 2018, for netop at observere den her slags lyn, og som vi også har fortalt om i en tidligere episode af RumSnak, som jeg nok skal prøve at huske at linke til, ellers så findes det tilbage i feedet i sæson 2, 3, 4 stykker. Noget af den stil. Ja. Der skal selvfølgelig også, Tina, lidt bonus på bordet, og denne her gang, der linker vi fra vores show notes til en artikel om en ny metode til at indfange og fjerne rumskrot. Mm-hmm. Rumskrot, gamle satellitter, raketrester og andet affald i omløb om kloden, det er jo et problem, vi har talt om flere gange, og det er også en udfordring, man stadig arbejder på at takle. Det er ikke et løst problem. Men en mulig metode er en slags hverdagsversion af det, som du garanteret er stødt på i science fiction, som man kalder for tractor beams. Mm-hmm. Altså ideen om en eller anden usynlig stråle, som kan indfange rumskibe eller asteroider eller andet ude i rummet, og ligesom trække det tilbage med sådan en usynlig stråle.
Altså der er noget Star Wars, der siger mig et eller andet, ikke?
Der er meget Star Wars over det her, ikke? Hen i science fiction, fiktionsland, der er det jo som regel noget med antityngdekræfter. Den slags, som vi altså ikke lige har fået styr på at lave herude i virkeligheden. Men nu er der altså nogle forskere, der har fundet på noget, der ligner, i hvert fald fra en overfladisk betragtning, og som måske kan bruges til at indfange og bortskaffe gamle satellitter og andet rumskrot. Og sagt helt kort, handler det om at bruge sådan et skraldebilrumfartøj, som er udstyret med en slags elektronkanon. Og den her kanon, den kan give et stykke satellitskrot eller andet rumskrot en negativ ladning, mens fartøjet selv har en positiv ladning. Og den her elektrostatiske tiltrækning mellem de to modsatte ladninger kan så gøre det muligt at fastholde og langsomt flytte et stykke skrot, og så anbringe det i en anden bane, eller måske endda give det et lille skub helt væk fra jorden. Og det synes jeg faktisk er en meget elegant teknik, som ikke gør, at det, der ligger deroppe, allerede skal være udstyret for eksempel med særlige magnetplader eller et eller andet, fordi det hjælper jo ikke med det, der allerede er deroppe. Det kan være, at fremtidige satellitter kan udstyres med noget, som gør det nemmere at indfange, men det hjælper jo ikke på de der tusinder af stykker rumskrot, der er deroppe i forvejen. Ikke?
Nej, jeg tænker, om det kan lade sig gøre på alt metal.
Det kan det givetvis ikke. Men,
det ved jeg heller ikke. Det er jo bare sådan, det jeg tænker nu, om man kan gøre det.
Og under alle omstændigheder er det heller ikke en metode, der kommer i brug i morgen. Men det er virkelig spændende at læse om. Det er en sjov idé. Og derfor linker vi altså til artiklen hos Life Science fra vores show notes.
Jeg har altså en anden god idé.
Ja.
Ballon, man gnider.
Okay, rumsnak slutter nu. Det var det. Hej. Det var hyggeligt. Du slukker bare mikrofonen, når du er færdig.
Okay, it's a nice ride up to now.
Fra eksploderende raketter og walisiske regnbuer til asteroidestøv og planetdannelse. I denne her episode, der har RumSnak-redaktionen altså været på udflugt på Center for Star and Planet Formation, som har til huse på Øster Voldgade i København, der hvor man også finder Geologisk Museum og en 20 ton tung meteorit, som hedder hvad?
Akpalilik.
Sådan. Centrets formål er selvfølgelig, som navnet siger, at gøre os klogere på, hvordan stjerner og planeter opstår, inklusive Jorden selv. Og netop Jordens oprindelse er fokus for en række nyere af Centrets artikler, som mener at kunne påvise eller sandsynliggøre, at Jorden blev dannet meget hurtigere, end man hidtil har antaget på få millioner år, i stedet for 50-100 millioner år.
Og for at høre mere om de her teorier, der besøgte vi for nyligt professor og centerleder Martin Bizzarro i hans lune hjørnekontor på StarPlan. Og vi fik også en kort rundtur i nogle af de laboratorier, blandt andet Kemilaboratoriet, hvor Martin og hans kolleger undersøger meteoritter og støvprøver fra asteroider. Martin er oprindeligt fra Canada, og selvom hans danske er aldeles udmærket, så tog vi altså interviewet på engelsk for ikke at krølle for meget rundt i simultan oversættelser mellem begreber og navne for forskningen.
Ja, og det er ikke svært at følge med i den her engelske snak. Men for en god ordens skyld, så tager vi lige en kort introduktion til nogle af de nøglebegreber, der dukker op i samtalen. Og jeg tænker, Tina, at du kan tage teten her og finde lidt info om planetdannelse frem fra din studietid. Nu har du allerede pralet af, at du har været på universitetet og alt muligt. Så, ja.
Ja, jeg havde også et par kurser om planetdannelse, hed det? Planetfysik, tror jeg bare, det hed.
Mm-hmm.
Så,
og hvad fortalte de dig der?
Jamen, på det tidspunkt, der var der store diskussioner om, hvordan planeterne i vores solsystem er kommet til at se ud, som de gør i dag. Altså, vi kan jo se, at vi har 4 små stenplaneter inderst, 4 store gasplaneter yderst, og så har vi nogle små klumper og noget is og sten, som er nogle dværgplaneter og asteroider osv. Men dengang, der blev vi undervist i, at planeterne sådan langsomt havde samlet sig til større og større sten, altså små sten stødt sammen til noget større, bygget sig op til protoplaneter, og så stødt sammen og dannet de her 8 planeter, som vi kender til i dag. Det store problem med den her teori, eller en af de store problemer, der er med den her teori, det er, at der så ikke bør findes vand i den indre del af solsystemet. Fordi hvis det har taget rigtig lang tid at danne planeterne, så kan vi have masser af is i udkanten af solsystemet, altså på den anden side af asteroidebæltet mellem Mars og Jupiter, men ikke noget herinde, hvor vi er. Og det betyder jo så, at nu hvor vi ved, at der findes vand på jorden, så burde vandet først være kommet til efterfølgende. Så det kan ikke have været i dannelsen af jorden, men det må have været kommet til efterfølgende. Det er det, man kalder late heavy bombardment-teorien. Mm-hmm. Og derfor er det også meget opsigtsvækkende, den her nye teori, som for tiden vinder indpas i videnskabelige kredse. Fordi ifølge den her teori, der har planeterne samlet sig meget hurtigere, og i stedet for at bygge sig langsomt op, så er de blevet dannet af en masse sten, metalstykker og vanddamp eller is, der er blevet tiltrukket af hinanden sådan ret hurtigt. Og det betyder, at så har der været vanddamp til stede i det indre solsystem, og så kan man have vand på planeter som Jorden. Det kalder man også for rapid accretion, altså hurtig ophobning eller hurtig samling. Så der er altså ret store perspektiver i den her nye teori, og det er altså det, som Martin fortæller meget mere om lige om lidt.
Ja, men før vi kommer til Martin, så det her var det store billede med planetdannelse. Men vi skal også lige nævne et par af de andre ting, som han kommer ind på i interviewet, bare lige for at sætte det op, så man kan følge med. Og isotoper, kan du lige kort introducere til. Isotoper, det er nok et begreb, mange kender fra deres skoletid, men alligevel for en god ordens skyld.
Ja, altså en af de ting, som er sådan meget fundamentale, når man snakker om planetdannelse, astrofysik i det hele taget, det er, at isotoper, det er varianter af grundstoffer, der adskiller sig ved mængden af neutroner i kernen. Og det vil for eksempel sige, at vi kan have brint i mange forskellige former, vi kan have kulstof i mange forskellige former. Og vi ved, at kulstof skal altid have 6 protoner i kernen, men så kan vi variere antallet af neutroner. Så der findes altså forskellige typer af alle grundstoffer. Det er sådan, at når vi ændrer antallet af neutroner i kernen, så påvirker det også deres stabilitet og fysiske karakteristika. Nogle isotoper er stabile og findes naturligt, mens andre de er radioaktive og henfalder over tid. Og derfor så kan forskere bruge de her forskellige typer isotoper til at kortlægge både tidslige og rumlige dimensioner, når det handler om fordeling af forskellige elementer i planeter og andre himmellegemer. Og det er altså noget af det, som Martin Bizzarro og hans kolleger de studerer nøje, både med teleskoper og i de kemiske laboratorier. Det
var isotoperne. Så skal vi også have styr på et begreb, som jeg tror færre mennesker har stødt på. Det var i hvert fald nyt for mig, da jeg begyndte at læse op på det her. Kondritter. Hvad er det for noget? Det er også noget af det, som Martin nævner et par gange.
Ja, vi slår bare lige op i
leksikonet. Ja. Tinapedia.
Kondritter, det er en type meteoritter, der stammer helt tilbage fra solsystemets begyndelse. Og kondritter, de udgør omkring 85% af alle meteornedslag her på Jorden. Så de er altså ret normale, men der findes forskellige typer af dem. Kondritter, de indeholder sådan små korn, der hedder kondruler. Og de her kondruler, de blev så dannet helt tidligt i den protoplanetariske skive. Og det er nogle af de ældste byggesten, der er i vores solsystem. Og kondritter, de kan så opdeles i forskellige grupper, for eksempel ordinære, karbonholdige eller akondritter.
Og I bliver hørt i det her bagefter. Jeg nævner det bare, så det er lige med at holde ørerne åbne, ikke?
I ender med en eksamen på 10 spørgsmål. Det er sådan også, at nogle af de her kondritter, de ser stadig ud i dag, som de gjorde for 4,5 milliarder år siden, da de blev dannet i den her protoplanetariske skive. Og de er en blanding af alle mulige forskellige grundstoffer, der ligger sådan lidt hulter til bulter. Andre af dem har været opvarmet og derved ændret sig. Fordi når man opvarmer noget, så sker der det, at de tungeste grundstoffer, som altså metallerne osv., de flyder ind mod midten, og de lette metaller, de vil ligge ud på overfladen. Det er faktisk det samme, som vi også ser her på Jorden. Der har vi jo en tung metalkerne, og så har vi de lettere stenarter på overfladen. Og det er det, vi kalder, at et legeme er differentieret.
Tak for det, Tina Ibsen-Pedia.
Var det sidste?
.dk. Nu skulle vi helst være blevet klædt på til interviewet med professor Martin Bizzarro, så lad os stille om til hjørnekontoret på StarPlan, hvor vi selvfølgelig også lige skal høre om, hvordan materialeprøver fra meteoritter, altså ting, vi har fundet her på Jorden, efterhånden også er ved at blive suppleret af støv og sten fra asteroider. Martin har tidligere været med til at analysere materiale fra asteroiden Ryugu og venter også på en lille leverance fra Bennu.
5, 4, 3, 2, 1... 0 and liftoff.
Yeah, so my name is Martin Bizzarro. I'm a professor at the Globe Institute, and I'm a leader of the Center for Star and Planet Formation. So my research is basically focused on understanding the formation of planetary bodies in our solar system and beyond. And I'm very interested in understanding the conditions when a planet forms that allow, for example, for water to be present or for the complex organic chemistry that can basically lead to life. So this is the potential habitability of planets. So that's a topic that interests me a lot.
Could you tell us a bit about the focus for the entire center as well? Is that aligned with yours, or is it completely different?
Yes and no. So basically, the Center for Star and Planet Formation, as it says, basically it's to understand the formation of stars and planets in general. And what is special about the center is because it's multidisciplinary. So we have people who are looking at rocks, at meteorites like me. We call them cosmochemists. So these researchers extract information from ancient material which was formed in the first few million years of the solar system. So these rocks are like time windows into the very beginning of our sun and its disk. There are people who use supercomputers to understand how planets come together. So astrophysicists, theoretical astrophysicists. We have astronomers, which use telescopes to look at young stellar objects or young stars surrounded by a disk of dust and gas, where the planets are basically emerging. And finally, we have people who look for exoplanets, so planets beyond our solar system. And the magic is that we have all these different disciplines interacting together.
And in the center here, you do most of these different kinds of research. Your particular interest is looking at those samples, correct?
Yeah, I mean, meteorites, this has been the focus of our research for the last 10 years, but now I've actually had material from the Ryugu asteroid by the Japanese Space Agency, which collected material in 2020, and we had this material, at least some of this material here at the center early in 2021. And now we're preparing for samples from Bennu, which are back on Earth now, and hopefully early next year we will have material from that as well.
So both of these missions, one from Japan and one from NASA, how do you get your hands on these samples? Are you just good friends with people, or is there a network of everyone working together?
So basically, with respect to the Japanese Space Agency, I was chosen to be a team member. And my task was to analyze one special element amongst, in the periodical table. So we were asked to measure the magnesium isotope composition of these samples, because this is something that we've established in our lab many years ago, and we're one of the best places in the world to do that. But for Bennu, I'm not part of the mission for Bennu. However, we published this very interesting paper in 2023 describing a new nucleosynthetic tracer, which is the isotopic composition of the element silicon. And silicon is like a building blocks of planets. Just like carbon to life, silicon to a planet is the major amount of material in a planet. And because we published this high impact paper this year, it got a lot of attention, and someone who's part of the mission actually asked me if we would be interested in measuring the silicon isotope composition of samples from Bennu. And so obviously I said yes, because I mean, it's a historical moment when you get this material. There's a funny story with the Ryugu samples. This was in 2021. I was basically, I was contacted by JAXA, and they told me the samples will soon be on their way. And we've arranged for them to arrive in Denmark on a particular date. So just be sure you're in the lab and to retrieve them. And so I was waiting that day in the lab, and I was very anxious, and I was imagining, so, is it going to be like a bulletproof truck that's going to come, and there's going to be a Japanese person with a with a box made of gold and white gloves and deliver the samples? And then it was 4:00, and I still haven't heard of anything, so I'm a bit worried. And then suddenly I get a text on my phone, and it was from PostNord. And PostNord said, well, we've tried to deliver your package from Japan, but we couldn't find you, so you can pick it up tomorrow at Furtex. And so I have a picture of me, because it was the first time this material arrived to Denmark. I have a picture of me at Furtex getting the samples from this teenage kid, which is like the person at the
How do you clear something like that in customs? I guess like samples from space.
I think they just send them by courier, but when it changes country, then it's PostNord. It came in the hands of PostNord. So now I've actually was awarded more material from Ryugu, and this time I'm just going to go to Japan, pick it up myself, and bring it, because you never know what can happen.
I wonder, did you tell that teenage kid in Furtex what he had just delivered to you?
Yeah, I did. I said, these samples come from outer space, and he just looked at me like, yeah, right.
Og lad os så vende os mod et af de store spørgsmål, som støv og sten fra asteroider og meteoritter måske kan være med til at svare på, nemlig hvordan Jorden egentlig blev dannet. Der findes altså basalt set 2 forskellige teorier, som Martin også fortæller. Den ene siger, at Jorden blev skabt langsomt over op til 100 millioner år, primært ved at lidt større himmellegemer ramlet sammen, mens den anden og nyere teori siger, at det er sket relativt hurtigt gennem en slags tyngdestøvsugning af millimetersmå stykker sten og is fra det tidlige solsystem på få millioner år.
So there's basically 2, I would say, n-member theories for the formation timescales of terrestrial planets. The classical one is that planets are formed by the slow collisional growth of planetary embryos. So bodies, say the size of Mars, slowly collide together, and it takes about 50 to 100 million years to have a planetary system. The other theory is the one that's called pebble accretion. So this is the very, very rapid accumulation of small millimeter-sized solids during the first few million years of the evolution of a planetary system. So in that framework, you make planets within a few million years. So it's very rapid. And one important, I would say, implication of this is that if planets are formed by slow collisional growth, they form at a time where there's no more gas in the disk, and it means that the water has to come from an external source. If you form planets very early, you form planets in the epoch where there's a snow line, so an area in the disk where around the protosun, an area where the water exists as solid or as vapor, and that snow line slowly migrates inward with time. And it means that at one point, the snow line is actually more or less in the same region where Earth formed. And so Earth can acquire its water by the accretion of what we call pebble snow. So these small ice particles, which will basically be like those little stone particles, they will be accreted by the proto-Earth. And so we've been working towards this, these ideas. This started in 2018, the first paper in Nature, where we basically suggest that the Earth could have formed very rapidly. 2020, another paper in Science Advances, where we measured the iron isotope composition of the Earth, and that also pointed towards this very rapid growth. And in 2023, by developing this new nucleosynthetic tracer, now we think we basically are very, very sure that this must be the way the Earth formed, by this very rapid accumulation of these small stone-like particles. And this is by measuring, again, the silicon isotope composition of the Earth and different bodies in the solar system, which tells us that the Earth is a mixture of material which form in the inner part of the disk and material which comes from the outer solar system. And so that can only happen if basically the Earth accreted some of these small stones which were from the outer disk coming towards the inner solar system.
Yeah, and it has quite a few consequences if water was actually here when Earth was formed, because of course one of the things I remember from my planetary physics classes were that we didn't know how water came to the Earth. We maybe thought that it was late heavy bombardment almost 4 billion years ago, and that made a lot of people kind of suggest that maybe water couldn't be found in other planetary systems in the habitable zone.
Yeah.
But of course, if it's possible to form water here, then the possibility for water on other habitable planets increases quite a bit, right?
Yeah, exactly. I mean, in the traditional theory, you need a stochastic sort of event, like a migration of the gas giants, and then you throw in these water-rich asteroids from the outer solar system, which contain water ices, and that impacts a planet and delivers basically an inventory of volatiles. If, on the other hand, the accretion of water is just a byproduct of the normal formation of a planet, then it means that there should be water worlds everywhere. And in fact, one thing you have to remember, the outer solar system, bodies in the outer solar system, they're like super rich. They have 10, 15 to 8% water. The Earth only has 500 ppm, 500 parts per million. So it's a very small quantity of water the Earth has compared to the outer solar system. So we think the Earth is water rich, but in fact it's water poor.
How did you come upon this theory? It's quite new, it would seem. What made you think in that direction?
So to give the proper credit, the theory of pebble accretion is something that has existed before we published our paper. So the person who is responsible for developing this theory is Anders Johansson, which he's a co-author of that Nature paper we published in 2023. But the theory of pebble accretion was basically developed to explain how the gas giants form. Because remember, the gas giants, they are made of an inner rocky core, but they've also attracted the gas which was present in the nebula. And because traditionally, the one basic problem was that it took too long to make the gas giants by traditional models, so that you've made them when there was no more gas. So you need another mechanism to form the gas giants. And they developed the theory of pebble accretion, which they were able to form the gas giants within only a few million years, and that could explain. the observation that we have in our solar system. Now, people have not applied the theory of pebble accretion to the formation of terrestrial planets, and that is something that we've been doing here together with Anders. We have a theoretical paper published in 2021 where we show that it's possible to make the Earth and the planets in the inner solar system by pebble accretion. So that's a theory paper. In the 2023 paper, we show that basically the isotopic composition of the Earth and other bodies in the solar system are consistent with pebble accretion. And so now we think we have both theory and observation that allow us to say confidently that the Earth must have formed very rapidly.
And Martin, can you go into a bit more detail about how you gathered evidence for or supporting material for this accretion theory?
You're familiar with the concept of DNA, where we can actually look at genetic relationships between populations or people by looking at their DNA. When the solar system formed, imagine that it was not totally homogeneous in terms of its composition, and that's because the cloud from which the solar system formed, so the cloud, part of the cloud collapsed to have a young stellar object, a protosun and a disk, and that cloud is made basically of stardust. So these stardust grains which are made in dying stars, and that's the material you start with. And it would be just like if you make, if you have a dough and you make buns, and then you have different kinds of seeds in your dough, and then you just make 8 different buns. You will never have the exact same amount of seeds in each of these buns. There'll be some small variability. And so we can use the isotope composition of bodies a little bit like DNA, because there's some small variations. And we use, for example, the isotopic composition of silicon or other elements to trace genetic relationships between different planets or solids, asteroids, and planets. And that's basically how we can come up with a way of understanding the nature of the precursor material. We can say the Earth has an isotopic signature or an isotopic DNA fingerprint that is somewhere between the inner solar system and the outer solar system. So it must be a mixture of the two. And that's, to make it simple, that's a bit the way we use these isotopes to understand what planets are made of and where the material was originally located, where it came from.
Yeah, and so how do you know where it originally came from? Do you have kind of the blueprint of the disk when it formed? Or how do you kind of compare what is the composition of the Earth now and where should it then form?
Yeah, so we have a sort of a general understanding of, as you say, a blueprint of the disk, because we can actually date bodies and look at their signature and basically have a sort of compositional map of the solar system. For example, some of the asteroids that we have, they're molten. And the reason they're molten is because they accreted very early, and there was short-lived radioisotopes in the early solar system. These are isotopes which basically decayed very rapidly within a few million years. And the energy released by these isotopes was enough to melt a small planet or a small body of like hundreds of kilometers in diameter. So we know that when we have a meteorite that comes from an asteroid which was differentiated, it must have formed in the first few million years. And must have formed in the inner solar system because it's water poor, for example. Then we have samples of carbonaceous chondrites. So these are chondrites which are rich in volatiles, and they're not differentiated, and so they're very pristine. And we can see that the temperature in these meteorites never was more than 50 degrees Celsius, for example. So they must have formed in the outer part of the solar system, and at a later time. So we have two pieces of information. We have space and time, where we can actually measure the isotopic composition and assign a particular value to this time and this place during the evolution of the protoplanetary disk. So we have a sort of compositional map in space and time of the protoplanetary disk.
Så Martin Bizzarro og hans kolleger mener altså, at Jorden er dannet af bitte små stykker sten og is, der på få millioner år har samlet sig til en klode. Og det er jo i sig selv spændende nok, men hvis det er rigtigt, har det altså også store perspektiver for vores forståelse af mulighederne for liv i resten af universet.
The most important aspect of the rapid formation of the Earth, if that's correct, then it implies that there would be potentially habitable planets everywhere in the galaxy. There are billions of Earth-like planets in the Milky Way only. And imagine, the possibility if all those planets have water, or at least some water on them, the possibility that life exists elsewhere is greatly enhanced if water is a byproduct of the accretion of planets in general. So the next question is prebiotic chemistry. So how does that come to the Earth? And that's a bit more complicated, because if the Earth, for example, our Earth went through this stage of having a giant impact which formed the Earth-Moon system. So if there was any life at that time on the proto-Earth, it must have been extinguished by this event. Because the gravity of the Earth is so strong, even if the water that previously existed on Earth went into vapor phase, it recondensed on the Earth after that. However, the organic molecules could have been destroyed. And so that remains to be understood, how were these organic molecules delivered to the proto-Earth after the giant impact that formed the Earth-Moon system. And the possibility is micrometeorites. As you know, micrometeorites, these are the small hundreds of microns, so fractions of millimeter size material that falls on the Earth every day. And the amount of mass that falls on the Earth via micrometeorite is a factor of 10 greater than these meteorites that you see here. There's just much more of them. And there was much more in the past as well. And so we think that these micrometeorites come from the comet-forming region where there's a lot of organic material. So it's possible that these micrometeorite showers delivered some organic material to the proto-Earth. Today, on average, there's about 1 micrometeorite per year per square meter. And that's why people have found them on the roof of various places in Denmark or in the world, in fact. We recently acquired approximately 100 micrometeorites from this Norwegian person, John Larsen, who has collected these objects. And we will actually determine, because silicon is a major element, we can use one single micrometeorite to determine its silicon isotope composition. That will allow us to better understand where they actually come from. And if they indeed come from the comet-forming region, then this will strengthen the idea that these objects can actually deliver organic material to the proto-Earth or protoplanetary bodies in general.
Okay, so next step is now we have water. Where does life come from?
Where does organic molecules that can lead to life come from? Exactly, yeah.
How has your theory been received by the research community?
If you go to the astronomy community, most people think this is correct. So the astronomers are very much behind this new theory, and they support our results. If you go to the cosmochemistry community, the people look at meteorites again, it's a bit split. So it takes, I think you have to remember that especially in the field like meteoritics, it takes time before new theories are accepted. And I think it's going to take between 5 to 10 years before this theory is fully accepted within this community. More than 10 years ago, we published a paper which basically said that the chronology of the solar system was wrong, and we had to establish a new chronology because of some details of the abundance of radioisotopes in the early solar system. We said these radioisotopes were not homogeneously distributed, meaning that you can't use them as a chronometer. So people said, no, that's not possible for many years, and now it's basically accepted more than 10 years after. And so I think it takes some time when you radically change the thinking of people before your theory is accepted. It takes some time, and it's going to be the same for this new paper here.
And of course, the more evidence you get behind it, the more accepted it will become.
Exactly, and I think that one of the challenges is that there's many elements for which you can look at. Silicon is one of them, calcium, iron, and you have to come up with a theory that unifies all the observation. And that's the big challenge. And that's what we tried to do in that 2023 paper. And I think we have now a unified theory which allows us to explain all the different nuclides and why the Earth plots here in this field and plots there in the other field. And so I think we have an understanding now, and there's so many new ideas in this paper that some of them are proof of concept. And now we need to go to the next level and show with more experiments, more simulation, how this exactly happens. But that paper basically pointed towards this direction where we should be heading for the next 5 to 10 years in this field.
We talked a bit about the Bennu samples earlier from Osiris Rex. What do you hope to gain from having access to those?
So I guess for me it's to compare Ryugu and Bennu because one of the big discovery, I would say, or perhaps the biggest discovery when we landed on Ryugu and took the samples back, it is that it looks very, very similar to one of the rarest type of carbonaceous chondrite that we have in our collections. These are called CI chondrites. So for Ivuna is a type of chondrite, or is the name of a chondrite, which is the type specimen for the CI chondrites. And these chondrites are essentially made of matrix, just dust particles. There's no inclusions or high temperature component, and they're very fragile. But what are the chances that the first asteroid, carbonaceous asteroid that we land on is a CI chondrite, I should say? The chances are it's not possible. So it must mean that this material is widespread. So if we go to Bennu and it's the same thing as Ryugu, it means that this material is widespread in the asteroid belt. And the fact that these meteorites do not reach the Earth is because they get destroyed in the atmosphere through the heating process. And it basically tells us that there was a major dust reservoir, which was like Ryugu and Bennu in the early solar system, and that possibly contributed to the volatile inventory of the terrestrial planet because this material is volatile rich. So if the Earth, part of the Earth's accretion formed by the accumulation of small Bennu or Ryugu-like particles, that basically delivers the volatiles that we have on Earth.
So we've been talking a lot about asteroids now, but in 10 years' time, we'll get a sample from Mars and the Perseverance rover as well. That's something you're interested in as well. Martin, can you tell us why this is interesting?
I think everyone agrees that Mars formed very rapidly. So, and this is research that's from other groups, but also from our group, that Mars solidified within the first 10 million years of the evolution of our solar system and had a crust since that time. And that means that because there's no plate tectonics on Mars, we preserve a record of the very early evolution of the planet. And Mars had water on its surface. Some of the research we've done recently showed that there must have been at least 300 meters of water covering the entire planet at one point in time. And so I would say that Mars was potentially habitable before the Earth was because of the giant impact. And so we're talking about perhaps 100, 150 million years before the Earth was potentially habitable. Mars was already potentially habitable. And so life could have actually started on Mars as opposed to started on Earth. So that's why I think it's really interesting to go to Mars, take samples, because if we can show that life was present on Mars, then we can compare, at least at one time, if life was present, we can determine whether or not life originated independently on Earth and Mars. There's no genetic relationship. And if that's the case, if life originated twice in our solar system, then of course it must be widespread in the universe. So that's a question for me that's really burning is, was there life on Mars, and is it independent than life on Earth?
Og det fortalte altså her professor og centerleder Martin Bizzarro fra StarPlan på Københavns Universitet, som også fortsætter sin forskning blandt andet som Villum Investigator med 30 millioner kroner i ryggen til Planetary Habitability-projektet.
Det er sådan et svært ord at sige, habitability.
Jeg synes, det gik meget godt.
Det gik meget godt. Jamen, du gør det godt.
Tak.
Hvis du vil vide mere om de ting, vi har talt om i den her episode, så husk at tjekke vores show notes til podcasten, hvor vi linker til mere information om både raketaffyringer, trackturbines og planetdannelse.
Og så nævnte vi også i begyndelsen, at Martin gav os en lille rundtur på kemilaboratorierne på StarPlan. Og hvis du bliver hængende i dag, efter vi har sagt tak for denne gang, så kan du høre et lille sammenklip på 5 minutters tid, hvor Martin fortæller om processen fra at skære meteoritter i skiver til at lave kemisk analyse af deres bestanddele.
5, 4, 3, 2, 1, 0, and liftoff.
Og med det er RumSnak landet for denne gang.
Men RumSnak vender selvfølgelig tilbage snart igen med den sidste episode i 2023. Og det bliver en ganske særlig en, fordi vi vender teleskopet tilbage mod året, der gik, og ser på nogle af de største, vigtigste, særeste eller sjoveste begivenheder og nyheder fra 2023.
Hvis man i mellemtiden gerne vil vide mere om RumSnak, så kan man finde os på Facebook, Instagram og LinkedIn.
Og man kan også læse mere om os på vores egen hjemmeside rumsnak.dk, hvor vi også har en lille butik med Rumsnak merchandise. Så der er måske til en lille julegave eller to der.
Ja, det vil være en god julegave, tør jeg godt sige.
Bestemt.
Helt objektivt. Hvis man ellers har spørgsmål eller kommentarer til os her på redaktionen, så kan man sende en mail til info@rumsnak.dk eller skrive til os selvfølgelig på vores sociale medier.
Husk også, at hvis du synes, det har været spændende at lytte til Rumsnak, så er du meget velkommen til at dele med familie, venner og andre nysgerrige.
RumSnak er støttet af Novo Nordisk-fonden og bliver produceret af Podlab. Jeg hedder Anders Høgh Nissen.
Og jeg hedder Tina Ibsen. Tak for denne gang.
So tell us, Martin, where are you taking us?
First, maybe we can have a quick look here at this lab here.
Og så er der rundtur.
This is a sample preparation lab here. And this is where the journey of a meteorite actually starts, because we have to prepare the samples to bring them to the clean lab, and here all the mechanical treatment happens. Like, for example, you need to cut a meteorite with a saw. So this is, for example, a special wire saw. You can see this wire is a few hundred microns, and this goes back and forth on a meteorite, basically to cut a slice, which we can then look more carefully with a microscope, take smaller fragments of it to analyze in the clean lab. So mechanical treatment of the meteorites happens in this not so clean room here. And this is the first stage. The second stage, we can go to the next level where we go to a different lab where we can actually look at the meteorites in more detail using these microscopes here. And so that's, again, the second stage. After we've broken the meteorite either in slices or small pieces, we come to this lab here and use optical microscopes to actually make sure that the material we want to sample is actually been sampled. And then we can take them to the chemistry lab after that to dissolve the rocks, the meteorites, and then extract the elements that we need to extract to measure the isotope composition on a mass spectrometer afterwards.
And this looks, apart from the microscopes, perhaps pretty much like a workshop.
It looks like a workshop, except that the air that's being pushed in here is clean. Okay. And so, and this is the cleaner part of the room. This is the dirtier part. So the clean air is pushed in this direction here. Okay. So this is cleaner in theory. In theory, we should be we're not having our shoes here, but for the sake of this.
Well, let's just say that we have. People can't see, it's just audio, so of course we had on the right footwear. Yeah.
So now we're going to the clean labs. We have a very large clean lab in relationship to other research groups. So there's in the clean labs we have approximately 12 individual working stations. It means that 12 people can work at the same time. And what is neat about this is that every person that works in the lab can have their own spot. So it allows us to put a lot of time in developing new method, new approaches, because we have this liberty of having a lot of space.
And of course now, Martin, you mentioned this being a clean lab, so I suppose we shouldn't just go in and out willy-nilly. Is it better if we stay out, or?
Okay. No, we can go in.
Okay.
And then here we don't have, in principle, wait.
We can take our shoes
No,
off.
we can. So what we have here, we have these individual stations where you can sit and dissolve the rocks, the meteorites, with various types of acid. So liquid meteorite, which we then separate the elements from this meteorite using resin that's located in these small columns that you see here.
So that's sort of the end product, if you will, of the going through the three different labs, ending here in the clean lab in the plexiglass boxes.
So no, because this is the second to last. So we go in the clean box and we extract the element. And let's say that now in my beaker I have magnesium. I've extracted all the other matrix element, and what's left in my beaker is magnesium. Then I go to the mass spectrometer lab down in the basement and measure the isotopic composition of this magnesium. And so this is, I would say, if you say there's 3 steps that's involved: the sample preparation, so the lab we were just before. After that, it's the chemical purification. This is the lab we're in now. And finally, in the mass spectrometer laboratory, we analyze the isotopic composition of the elements that we're interested in.
Fantastic. That's down in the basement. We won't go there today, but that's the final stage of the process.
Final stage of the process, and perhaps the most exciting, because that's where you're sitting in front of the computer and seeing the numbers coming up, and that's where you have the result in front of you. Because when here you don't know, you're basically separating the element, and then it's when you're in mass spec lab that you get the isotopic composition and get excited. Yeah.
And thank you.